Solutions for quiz 3 from Math 252. This first one we're asked to determine this big mess, and given this hint, kind of implying that partial fraction decomposition will help. So I'm going to do that first. And the way you do partial fraction decomposition is you say, all right, this thing, this 4x squared plus 3x plus 5 divided by, and I'll go ahead and write the factored form of the denominator here, x squared plus 1 over x plus 1. That thing's got to be equal to a sum of two fractions, rational expressions really. One of them's x squared plus 1 and the other one's x plus 1. So what goes up on the top? Well, that's what you're trying to figure out. And so because this is a second degree irreducible polynomial, I need a first degree irreducible, or a first degree polynomial up on in the numerator here, and a 0 degree over here, I guess. So I get here. This is my partial fraction decomposition setup. And from here, what you can do is, well, wait a minute. Well, there's a few things you can do. If you got a common denominator on this side, then to get a common denominator, I would multiply this by x plus 1 over x plus 1. So I would have x plus 1 times ax plus b plus c times x squared plus 1. And then that whole thing would be over my common denominator of x plus 1 times x squared plus 1. But I don't even need to write that because note on this side of the equation I also have x squared plus 1 times x plus 1. So if the denominators are the same, then the numerators must be the same, meaning this must be equal to 4x squared plus 3x plus 5. If you don't like that logic, multiply both sides of the equation by this denominator. It'll cancel out here. It'll leave an x plus 1 up top here and an x squared plus 1 up top here and cancel these guys out. That gives me exactly this line. So now I got to solve for a, b, and c. I got an equation. Presumably I can do this. It'll help to get rid of all the parentheses, so I'll FOIL this out to get ax squared plus bx plus ax plus b. And then I'll FOIL, or distribute that c through to get c x squared plus c. And so if 4x squared plus 3x plus 5 equals this, then this term plus this term must add up to give me 4x squared. In other words, 4 must be equal to a plus c. Similarly, this bx and this ax, when I add them together, they must give me 3x. So a plus b must be equal to 3. And finally, my constants, I got a b and a c as constant terms and a 5 over here. So 5 must be equal to b plus c. And from here, I can solve for a, b, and c. A couple different ways you can do it. I think the easiest way to do it is just grab any two of these equations. Grab these two maybe. And subtract them. If this equals this and this equals this, then this minus this equals this minus this. But if I subtract this side, the a's will cancel out. And so I'll have 4 minus 3, in other words 1, is equal to a plus c minus a plus b, in other words c minus b. And what I can then do is take that equation and this equation, the 5 equals, instead of b plus c, I'm going to write c plus b. So it's a little bit more obvious on how I put these together. And the way I'm going to put these guys together is I'm just going to add them up. 1 plus 5 is 6. C plus c is 2c. Negative b plus b is 0, nothing. So I get 6 is equal to 2c, and therefore, maybe not equals, therefore, if you divide both sides by 2, you get that c equals 3. And if you know that c equals 3, go to, I don't know, maybe this equation. 1 is equal to 3 minus b. What must b be equal to? Sounds like 2 to me. And I don't know, to figure out a, pick your favorite one that has an a in it. Maybe this guy right here. A plus 2 more equals 3. So what number plus 2 more equals 3? It sounds like a equals 1. Get these three values, which allow me finally to start the problem, at least from a calculus 2 perspective. It allows me to say this thing that I'm trying to take the integral of is really the same as this thing right here, which presumably will be easier to take the integral of, except playing the role of a as a 1, b as a 2, c as a 3. So from here, I can say this is equal to the integral of, and then instead of ax plus b, I can write 1x plus 2 divided by x squared plus 1. Plus, and then instead of c, I'll write 3 over x plus 1 dx. And I could take this a step further. Well, how many steps do I want to show? I can break this up into x over this stuff plus 2 over this stuff. But if I break this up into x over this plus 2 over this, then I have a sum of 3 things, which I can break up into 3 different integrals. I can call this the integral of x over x squared plus 1 dx, plus the integral of 2 over x squared plus 1 dx, which I could write as 2 times the integral of 1 over x squared plus 1 dx, plus I could factor out this 3 and call this 3 times the integral of 1 over x plus 1 dx. 3 problems. You answer these 3, you're done. I think this one's the hardest, because for this one I'll want to use a U-Substitution, so maybe I should color code these a little bit. For this integral, which is now kind of illegible, I'll use a U-Substitution. I'm going to let u be equal to x squared plus 1, and therefore du is equal to 2x. And what that allows me to do is say that this is equal to the integral of, and if du equals 2x dx, then 1x dx equals half of du. So what I have is 1 over u times 1/2 du from this guy. From the second one, well, I guess I don't really need to do any U-substitutions for either of these two. Maybe it helps to see it on this one. The second one, I'm just going to leave it alone for now. This third one, the integral of 1 over x plus 1, you could probably do this without a U-substitution, but I'm going to show one anyways. Let's let u be equal to x plus 1, and then du is just equal to dx. So therefore, what I get out of this third one here is 3 times the integral of 1 over u du. And then this red guy is just kind of hanging out in the middle. I'm going to leave it as x's because I don't need any U-substitutions for this one, because this one happens to be exactly in the form that I know. I know the derivative of arctangent of x is 1 over 1 plus x squared. So I can figure this thing out. Let's see. So first this one, take the 1/2 out in front. And then the derivative of 1 over u du is the natural log of the absolute value of u. But u is x squared plus 1. So I can write this like this. For the red one, I got the 2 hanging out, and then I got arctangent of x. And then for the green one, I got the 3 hanging out, and then similar to this, I have the natural log. Yeah, similar to that. I have the natural log of the absolute value of u, but now playing the role of u is x plus 1. So I get to here. That's a perfectly good answer the way it's written. If you felt like it, you could use some log rules to put some stuff together. I'm not going to, well, should I show you that? You can do it. Fine. Or 2 arctangent of x plus, using log rules, I could bring this 3 up into the exponent, I could bring this 1/2 up into the exponent, and then I'd have the log of something plus the log of something else, which I can rewrite as the log of the product. So I can call this the natural log of the absolute value of x squared plus 1 to the 1/2 power, square root of, times the absolute value of x plus 1 to the 3rd power. Either of these are fine. I imagine that I don't think anyone in the class would rewrite it like this, so I'll go ahead and circle or square this first one here and call that my final answer. This one here, trig substitutions. The trick with this problem is to peel off a cosine, essentially. I want to do a trig substitution, so I see sines and cosines, so I'm thinking, all right, u is one or the other. But if you make u cosine, then du would be sine, or I guess negative sine. But the signs are down in the bottom, so that's not going to help you. So really, this trig substitution you're going to want to do is we're going to want to let u equal sine of x. And then du will be equal to cosine of x. And you're like, but wait a minute, you got cosine to the 5th here. True, but I can rewrite that as cosine to the 4th x, or maybe even do 2 steps at once and call it cosine squared x squared, and multiply that times cosine of x and divide that by sine to the 4th x dx. And why did I bother doing all that? Well, cosine squared is the same as 1 minus sine squared. So instead of writing cosine squared x inside the parentheses, I can write this and then later square it. And that's divided by sine to the fourth x. And then I got this cosine x dx, which I'll write down here to really emphasize that I'm going to do a U substitution. U is equal to sine of x, and therefore du is equal to cosine of x. And so really what I'm being asked is, what is the integral of 1 minus u squared squared over u to the fourth power du? And that's an integral I can evaluate maybe after I do a little bit of algebra. Let's FOIL out the top to get 1 minus 2u squared plus u to the fourth power divided by u to the fourth power du. And I can rewrite this as the integral of u to the negative fourth power, that's this 1 over u to the fourth, minus 2 times the integral of u to the negative 2 power. Took this negative 2, brought it in front. U squared over u to the fourth is u to the negative 2 power here, plus the integral of just 1. Oh, and all these have to have du's on them. Ugh. du, d, okay, just go back and erase. Sure you knew what I meant, but I should not make the solutions dependent on you knowing what I mean. Should actually do things right. So when I break this into multiple integrals, I need multiple du's. Get something like this. And yeah, you don't even have to write that 1 if you don't want to, but I think it helps as a placeholder. So let's go taking some antiderivatives. U to the negative fourth, a new exponent would be u to the negative third, but if I don't want a coefficient, I have to do this 1 divided by negative 3 out in front. And same idea here, I got minus 2. My new exponent is going to be u to the negative 1, but if I don't want that coefficient, I have to have 1 divided by negative 1. And then the antiderivative of 1 is just u. And I can clean this mess up by calling it, I don't know, negative 1 over 3u cubed. Minus 2 and this minus cancel each other out and just make it 2 over u plus u. But u is a figment of my imagination. U is really sine of x. It's something I created, so I best to get rid of it. Got negative 1 over 3 sine cubed of x plus 2 over sine of x plus sine of x plus c. Yeah, no. And if you felt like you could go get in common denominators and see if you could do some trig substitution, actually you could. If you got a common denominator here, I think you'd multiply the top by sine squareds, and then maybe you can do something with sine squares, changing them into cosine squares, and maybe that would help you simplify stuff. But I'm not worried about simplification. I'm going to leave my answer just like this. Moving on, figure this mess out. Hint, use the tables. Okay, the table that you'll want to use, or the equation in the tables that you'll want to use is 47. Tables number 47. And what number 47 in the tables tell you is that the integral of u du divided by a plus bu is equal to 1 over b squared times a plus bu minus a natural log, this is a mess, of a plus bu, and my natural log, and my parentheses tack on a plus c. This is what the tables tell me. You know, how the hell am I going to use this? I have a 2x plus 1 up in the numerator. I just want u du here. We'll do a trig, or do a substitution. Let's, maybe in a different color, let u be equal to 2x plus 1. Well then du is equal to 2 dx. In other words, half of du is equal to dx. So let's go try and sub that in. I get from here, I get the original question is equal to the integral of 2x plus 1, which I'm calling u, divided by 4x plus 3. How am I going to deal with that 4x plus 3? Well, I'd like to write that 4x plus 3 in terms of 2x plus 1s. Maybe I'll say note to u. How about I'll write this down here? If u equals 2x plus 1, then 2u must be equal to 4x plus 2. Oh, so close. I wanted 4x plus 3. All right. 2x plus 1. Whoa, 2u plus 1. Sorry, I said u, but I wrote x. At least I hope I said u. if u equals 2x plus 1, 2u should be equal to 4x plus 2. And therefore 2u plus 1 will be equal to 4x plus 3. And now what I can do is go and rewrite everything. 2x plus 1 is just u. 2u plus 1 is 4x plus 3. And then dx is 1/2 du. So really what I have is 1/2 the integral of u divided by 2u plus 1 du. And now it fits this form pretty nicely. Playing the role of a is 1, and playing the role of b is 2. So what I can do is copy this. I can say I still got that 1/2 out in front and then some parentheses. I'm going to try my best to rewrite this entire thing, except in place of b's I'll write a 2 and in place of a's I'll write a 1. So that'll give me 1/4 times 1 plus 2u minus 1 times the natural log of a plus bu, which is 1 plus 2u. In these parentheses. And then I guess I can end those parentheses and tack on a c here. Okay, but that's in terms of u's, and I should have my answer in terms of x's, so I guess my final answer would be, I can combine the 1/2 and the 1/4 and call that 1/8 times, and then I have 1 plus 2 times, and then in place of u I can write 2x plus 1 minus the natural log of 1 plus 2 times u, which is 2x plus 1. And then in these parentheses and tack on a c. And I think I can even clean that up a little bit if I was so inclined. 2 times 2x plus 1 is 4x plus 2, plus 1 more would be 4x plus 3. So I got a 4x plus 3 coming out of here, minus the natural log of, and then same thing here, this is going to be 4x plus 3. And you're like, oh, you forgot about that 8. No, I didn't. Let's divide the whole thing by 8, and then tack on a c. But really, I don't care which of these forms you give me. Either of these are totally fine. As is any other equivalent form. Maybe just as a note, could avoid the tables by doing integration by parts, by doing integration by parts. But it ain't pretty. You make u equal to, here's my original equation, 2x plus 1, and therefore dv must be equal to 1 over 4x plus 3. So then I got du is equal to 2 dx, and v must have been equal to, well, let's see, if I had the natural log of 4x plus 3 and took that derivative, I'd have an extra 4, so it would be 1 over 4x plus 3 times 4. But I don't want that extra times 4, so I better put a 1/4 here. You could do integration by parts using all these things. The problem is in the integral of v du, you'll be taking the integral of the natural log. And unless you have that memorized, you're either using the tables or using integration by parts again to figure that all out. Okay, number 4. The trick for number 4 is to recognize that you have an improper integral here, the integral from 0 to infinity. You can't plug in infinities. Really what you're going to have to do is rewrite this as a limit. Say that this is equal to the limit as b approaches infinity of the integral from 0 to b of x e to the negative x dx. And so the way I like to do these, well, first of all, we're going to have to take this integral. And taking this integral, I think we'll do integration by parts. And it's kind of messy doing integration by parts when you have a definite integral like this. So what I'm going to do, kind of off to the side maybe, is let's first just figure out the integral of x e to the negative x. And I'm going to use integration by parts, so let's let u be equal to x, and therefore dv must be equal to e to the negative x dx. And yes, I should be putting a dx right here. And if u equals x, then du is just equal to dx. And if the derivative of some function v was e to the negative x, then that function would have been negative e to the negative x. And so really, this integral is equal to, using my integration by parts formula, u times v, so negative x e to the negative x, minus the integral of v du, this times this. I can pull that negative out in front and make that positive, and this e to the negative x dx. Now I can say negative x e to the negative x plus this integral, which is negative e to the negative x. And so you have this integral plus c, I suppose. And using that information, you can come back over here and say, okay, so really this is just the limit as b approaches infinity of this mess that I just figured out, negative x e to the negative x minus e to the negative x plus c, which I don't even need to write because I'm going to evaluate it from 0 to b. Something like that. Okay, so let's evaluate this thing. Limit as b approaches infinity. If I throw in a b everywhere I see an x, I get negative b e to the negative b minus e to the negative b. And from that I want to subtract whatever I would get if I threw an x or a 0 in everywhere I see an x. That'd be 0 minus 1. 0 from this term, negative 1 from this term. And so really what I'm trying to figure out is what is the limit as b approaches infinity of negative b e to the negative b minus e to the negative b plus 1. Evaluating this integral, there's a couple ways you can do it. I think the easiest way, or at least first thing that came to mind for me, is break this up into two different limits. This is the limit as b approaches infinity of negative b e to the negative b minus e to the negative b plus the limit as b approaches infinity of 1. Wait, the limit as b approaches infinity of 1, there's no b's here, right? So this thing right here is just equal to 1. What about this thing over here? Maybe I need more room. The limit as b approaches infinity of, how about this? Circle this first one here. Then I'll deal with that up here. And say that that's equal to the limit as b approaches infinity of e to the negative b. I could think of as being down on the bottom of this fraction. So I got negative b minus 1 divided by e to the positive b. And then this is a limit I think I can evaluate using L'Hopital's rule. Been a while since we thought about that. Because it's an indeterminate form. As b approaches infinity, this is big over big, or I guess negative big over big. So you have an indeterminate form, you use L'Hopital's rule. L'Hopital's rule tells you that the limit of this quotient is the limit of the derivative of this divided by the derivative of this. Well, the derivative of the top is just negative 1. And this limit I can evaluate because this is negative 1 over big, in other words 0. As b gets really, really large, e to the b gets really, really large, and negative 1 over something really large is 0. So what I end up with here is 0 plus 1, all that just to figure out that the answer is just 1. Kind of crazy that that answer is 1, but whatever. Moving on. Find the area of the shaded region below. All right, so this is tricky. What you have to first recognize is that we're going to have to change our variable of integration. Because my x-coordinates go from, what, negative 3 to 5, but on this region in here, the top curve and the bottom curve are the same curve, so I'd have to get kind of clever and like break it up into two different ones. I don't want to do red minus blue on this region because I don't want this area in here. So while you could do it integrating over x, it'll be a lot easier integrating over y. I could say that this is the integral from, it looks like my y-coordinates go from negative 2 up to positive 4. Is that true? I think this is positive 4 right here. I should probably check and make sure that's true. Things work out fine. I think this point right here is 5, 4. And the way we can check that is if x equals 5 and y equals 4, that satisfies this equation. If x equals 5 and y equals 4, does that satisfy this one? Well, 4 squared is 16, and half of 16 is 8, and 8 minus 3, sure enough, is 5. So this point right here is 5, 4, as it kind of appears to be. And what that tells me is I want to integrate from -2 up to +4. And then I have to figure out which curve is kind of on top and which one is on the bottom. Well, by on top, I mean the first has the larger x-coordinate. And so that's this blue curve right here. So what I want to do is take the blue curve and solve it for x. Well, fortunately, it already is, so it would be y plus 1. And from that, I want to subtract the red curve, which is 1/2 y squared minus 3. And then this integral will end up being this area. So let's see, I got the integral from -2 to 4 of, can I clean things up at all? I guess I could write these terms in order. I don't know that that's important. -1/2 y squared plus y from here. And then I got a minus 3, that's hard to read. So that's plus 3 over here and plus 1 more, so I got a plus 4. And I can evaluate this integral. This new exponent should be a 3. I got -1/6 y to the 3rd power. You can check that by taking the derivative, making sure you get back up here. Plus 1/2 y squared plus 4y. And I guess plus c, or you can leave off the c because you're going to have to evaluate this from -2 to 4. So now you go plugging in numbers, you plug in a 4 and you get -1/6 times 4 to the 3rd power, which is what, 64? Plus 1/2 times 4 to the 2nd power, which is 16, plus 4 times 4, which, yeah, again, that's 16. This is what you get when you plug 4 in. What about when you plug -2 in? Well, I'd get -1/6 times +4, -2, nope, times -8. And then plus 1/2 times +4. And then plus 4 times -2. I'm going to rewrite that so that people can actually see what I wrote. And so now you just got to do some calculations here. 64/6, yuck. Maybe we call that 32 over 3. And it's negative, and then this one is 8, and then this one is 16, and from that I want to subtract 1/6 times 8 is 8/6, which is 4/3. These two negatives cancel, but I got to subtract it, so I got minus 4/3. 1/2 times 4 is 2, but I want to subtract it. And 4 times -2 is -8, but I want to subtract it, so I got plus 8. And so what do I end up with here? 8 and 16 is 24, and 8 more is 32. Minus 2 gives me 30. And if I combine the thirds, I got -32 thirds minus 4 more, so I have minus 36 thirds. So I got 90 thirds minus 36 thirds. I have, what, 54 thirds? Hey, that's kind of convenient, because 54 thirds is 18. And I guess I could have figured that out up here. Maybe it would have made more sense to say this is 30 minus 12, which is 18. Quicker way to the answer, if you don't like fractions. At any rate, what that tells me is that this area right here is 18. Seem reasonable? Well, there's 1, 2, yeah, 2.5, 3, 4, 5, 6, 7, 8. Yeah, I guess I could see 18 in there. Call this good.